I'm going to take a look at example 5 now in solving trig equations. This one we've got a mix of tangents and cosines. Just like on the last one we had a mix of secants and cosines. But here's another thing that we want to look at that gives me pause in this problem. The tangent has an argument of x, whereas the cosine has an argument of 2x. So these are really not very similar things at all. They're not combinable. What I want you to think of when you see something like this, don't jump into trig identity mode. Just think about this as an expression, I'll call it A, and this as a completely different unrelated expression called B. Now, of course, minus, this is the exact same B value again, so this is A times B minus B. So thinking about this in a pure algebraic mindset, we can see that we've got two terms. AB is the first term, and negative B is the second term, and they share a factor. Obviously, they share the factor of B. So we can actually factor out the B from the first term and from the second term and realize that what's left in the first term is just A, and then what's left in the second term is just negative 1. Always ask the question, if I were to distribute this B back into the parentheses, will it take me back to where I started? And the answer, of course, is yes, so we're factoring correctly. So since I factored out a B, and B is cosine of 2x, let's factor out the cosine of 2x. Do you have to write the stuff in red down? Absolutely not. But you should have that in the back of your mind when you're factoring. So anyway, from the first term, we're left with just the tangent of x. From the second term, we're left with just minus 1. People like to forget that negative 1. They think, oh, if I take this out, then it's completely gone. But if it's completely gone, then when I distribute it back in, I wouldn't get my cosine of 2x back again. So let's remember that we still have equals 0 on the right side, right? This is an equation still. We've got a left side and a right side. So this is great news because now we have a factored version of the expression on the left side of the equation. Cosine of 2x is one factor, and tangent of x minus 1 is a second factor. And when you multiply those two factors together, you get 0. The only way that's possible to multiply two things together and get 0 is when one of those two things is 0. So either the cosine of 2x is equal to 0 or the tangent of 1x minus 1 is equal to 0. So now we've got two baby equations that we need to solve. Over here, we're going to get rid of the cosine by inverse cosining both sides, so that cosine goes away, we're left with 2x. Notice that that's not 1x, it's 2x. The inverse cosine takes care of the cosine, but it doesn't take care of the 2. And we've got our two answers, right? So inverse cosine of 0 is, well, if we think about it, we're looking for an angle whose cosine is equal to 0. Pi over 2 fits that bill. And then since this is an even function, cosine is an even function, we have the positive version and we have the negative version. Now, if you wanted to in your head think, oh, this is the same, not the same, but it's coterminal to 3 pi over 2, then you can put 3 pi over 2 here instead. That's perfectly fine. Either or. But if we're getting all of the solutions, don't forget that we also have plus 2 pi n. Plus 2 pi n, we get all the coterminal angles, and that's going to include the 3 pi over 2 regardless. And of course, as always, n is an element of the integers. I'm going to hold off on that because I forgot I also have my inverse tangent. Well, whatever. I'll go ahead and write it now, I guess. N is an element of the integers. All right, but notice that I haven't solved for x yet. I've only solved for 2x. And we know to undo the multiplication, we need to divide. So we're going to divide 2x by 2 to get 1x. And if we divide the left side of the equation by 2, we better divide the right side of the equation by 2. So that pi over 2 gets divided by 2, and we get pi over 4. Don't forget about this. The 2 pi n is also getting divided by 2. So we get plus not 2 pi n, but plus 1 pi n, because 2 divided by 2 is 1. And if you think about back when we were graphing, that 2x for an argument was going to change our period, right? Instead of 2 pi being our period, we would get 2 pi over b, or 2 pi over 2, or 1 pi as our period. So it makes perfect sense that we're adding pi n to this because this term repeats itself every pi. Make sure we do that with the other solution as well. So negative pi over 4 plus pi n. And that's all the solutions from cosine of 2x equals 0. But we also have all the solutions from this other one. So this is the tangent equation. So instead of starting with the inverse, we have to deal with this minus 1 first, right? Because that's outside of the argument. It's not tangent of the quantity x minus 1. It's tangent of x, finish that up, and then subtract 1 from it. So to solve for x, we have to undo that minus 1 first by adding 1 to both sides. So we're saying, what can we take the tangent of and get 1? And I believe we've seen that a bunch of times. We've seen pi over 4, right? And in fact, we only need one answer here because tangent goes through 2 periods when we go from 0 to 2 pi. So we just have to remember that with tangent, we automatically add pi n. Right? So we've got a different rule for cosines. When we take the inverse cosine, we take the plus or the minus, but then we add 2 pi n to each of those 2 versions. For tangent, we don't do plus or minus. It's not an even function. Tangent is an odd function. But instead, we change this to a plus 1 pi n because the period of tangent is 1 pi. So if we take a look at all our solutions, we've got this is all our solutions. And then if we wanted to move on to the, what about if it's just between 0 and 2 pi? So including 0, not including 2 pi. If we look for those, we look at each one of these lists. You might notice that the pi over 4 plus pi n that we had for the cosine equation and the pi over 4 plus pi n that we got for the tangent equation are identical. So we really don't need them twice. In fact, let's go ahead and make this a little cleaner and just circle. I'll circle it in blue. That's all of them because this is a duplicate. That doesn't always happen, of course. It's duplicated between these two guys. So anyway, if we're just going to look for the finite list of values between 0 and 2 pi, start with the pi over 4. Pi over 4 is definitely between 0 and 2 pi. And if you'll notice, because we've got not plus 2 pi n, but just plus 1 pi n, we can actually add pi to this pi over 4 and get another answer that is between 0 and 2 pi. 5 pi over 4 is definitely between 0 and 2 pi. So this first line gives us 2 answers, not just one answer like before. All right, and then we move on to this next line. Oh, if we try to add one more pi, we'd get 9 pi over 4, right? And we'd say, wait a second, 9 pi over 4, that's no good because that's too big. That's bigger than 2 pi. So we don't want to include that. So that's how we know we're done with that first list. Second list, we take a look at that negative pi over 4, and that's too small. That's less than 0. So we don't want negative pi over 4. So we'll add 1 pi to negative pi over 4 to get 3 pi over 4. And that's all well and good. But then we should expect to get a second one because, again, we divided by 2 here. So if we add pi again to 3 pi over 4, we get 7 pi over 4. And if we added pi again, we'd get up to 11 pi over 4, and 11 pi over 4 is too big. So we stop there. So these are the finite list of values that are between 0 and 2 pi. And don't forget, you can graph these. If you graph this original equation, y equals the left side of the equation, that's equal to 0, which means we're looking for x-intercepts. And you should see between 0 and 2 pi, you should see these 4 answers between 0 and 2 pi.